Hello viewers, welcome to this video lecture on flip-flops. Flip-flops are the basic element of any sequential circuit. Let us start with the video with the detail of flip-flops. First of all, what is a sequential circuit? Sequential circuits are those circuits whose output at any time depends not only on the present input but also it depends on the past outputs, and they also need some type of memory to remember the previous output values. And for that memory element we use, these are the memory elements as you can see in the diagram. A combinational logic circuit along with the memory element forms a sequential circuit, and this memory element will be formed by the flip-flops. So a sequential circuit is nothing but it is a combination of combinational logic circuit and memory elements. So basically sequential circuits are of two types: synchronous sequential circuits and asynchronous sequential circuits. Synchronous sequential circuits are those circuits whose output changes only at some discrete instants of time, and that discrete instant is determined by a timing signal that is called as a clock, right? As you can see in the diagram, it is a 2-bit synchronous up counter is given. In both the flip-flops you can see this common clock is being used, and both these flip-flops will be working at the same instant of time. Whereas in asynchronous sequential circuits, the circuit output change at any time, that is the not dependent on the clock. Means the both the uh, flip-flops or the blocks in the asynchronous sequential circuits, they operate without a common clock. As you can see in the diagram, it is a 2-bit asynchronous up counter. As you can see in both the flip-flops, the clock in the first case it is determined by the clock, or it is dependent on the working of the first flip-flop is dependent on the clock, whereas for the second flip-flop the clock is provided by the complemented output of the first flip-flop. So the clock is not common to both the blocks in this asynchronous up counter. So let us start with the flip-flop. What is a flip-flop? That is being used as a memory element in the sequential circuit. So its basic function is to store one bit, either 0 or 1. So it has two stable states which contains the logic 0 and logic 1. Logic 1 means it has a flip-flop has two outputs. One, we can say that it is a normal output, and the other is the complemented output of the normal output. But the logic 1 determines that when the normal output is high, then it is said to be the logic 1, and that is the state of the flip-flop is at logic 1, and the flip-flop is said to be set, and in that case the complemented output is low. As you know, the output, as the name suggests, it is the complement output of the normal output. So whatever will be the normal output, the other output will be complemented of that. Another logic is the logic 0. In logic 0 output, or in that state, the flip-flop normal output is low, and in that condition the flip-flop is said to be reset, and the complement output is high, right? So there are basically four types of flip-flops. We can say SR flip-flop, that is also called as set reset flip-flop. Second one is delay flip-flop, that is made from the SR flip-flop, and D type flip-flop means delayed flip-flop is there. Third one is JK flip-flop, and to remove the limitations of JK flip-flop we have some improved JK flip-flop, that is called as master slave JK flip-flop, and the last one that is made from the JK flip-flop, it is called as the T flip-flop, which is said to be toggle flip-flop. Now as we have seen that the the types of flip-flops are there, and the flip-flop or any sequential circuit is dependent upon the clock pulse. So the clock pulse is there to operate the functioning or control the functioning of any circuit, any sequential circuit or any flip-flop. So in that case, the clock can set to be edge triggered or level triggered. The manner in which we are taking this clock, the instant at which the operation of the circuit will take place. So edge triggers can also be of two types. It is positive edge triggered or negative edge triggered. This is positive edge trigger and negative edge trigger. As we can see, when it is the rising edge is called as the positive edge and falling edge is called as the negative edge trigger. So when the changes in the flip-flop or the flip-flop operates at this edge, that is called as the positive edge flip-flop and it is the rising edge, right? So when the operation of the flip-flop takes place at the falling edge, or that is called as the negative edge triggered flip-flop. Another type of operation can take place at the levels of the clock. So it can be a level triggered flip-flop. So now this in the level triggered flip-flop, this for the whole duration there can be changes in the flip-flop can occur at any number of times. But whereas in the edge triggered flip-flop, the change in the output will take place only at these edges only, right? So clock pulse transition can be positive transition or negative transition. Similarly, the level sensitive, it can be positive level sensitive or zero level sensitive or negative level sensitive. It is less favored because depending upon the duration of the pulse, output may change a number of times during that level. Right. Next, starting with the SR flip-flop. As you can see in the SR flip-flop, we are using 4 NAND gates. In the case of NAND gate, we can also use NOR gates. So this 4 NAND gates are being used. This clock is used as the enable pin for this flip-flop. When this clock, if it is used as at the positive edge triggered, so when this clock is there, the at the positive edge side, the this flip-flop will be enabled to work. So it will operate in the case of positive edge only. For the level and the negative edge, this SR will act as a closed circuit. So in spite of the input available at the SR and the R input, if the clock is not enabled, this flip-flop will not give any output or no change can occur at the output. Similarly, you can see the inputs S and R are given at the gates 3 and 4 and the output from the 3 and 4 NAND gates are given to this 1 and 2 NAND gates. The output, the final output is fed back to these 2 and 1 flip-flops. This is the normal output of the flip-flop, that is Qn plus 1, or you can whatever you are writing, and this is Qn plus 1, but that is the complemented output of the normal input, right? So as you can see, this is the truth table is given and this is the block diagram of the SR flip-flop. Simple, this block is there, that is SR flip-flop, and the inputs are S and R. E is the enable which is provided by the clock, and there are two outputs Qn plus 1 and Q bar n plus 1. So as you can see from the truth table, when this enable pin is high, it is taken as high at the positive edge trigger, only then this output is coming. And as we have two inputs, so there can be four type of combinations can be there. SR can be 0 0 0 1 1 0 and 1 1. So when the S is 0, R is 0, the output will be, there will be no change in the output. whatever is the past output, Qn is the past output, Qn plus 1 is taken as the present output at the present instant. So there will be no change. No change means whatever will be the past output, that will be available in the present also. So when S is 0, R is 1, the output will be 0 and the complemented will be 1, and the flip-flop is set to be reset. When S is 1, R is 0, outputs will be 1 and the complemented output will be 0 and the flip-flop is set to be set. But when both the inputs are high, that is 1, then whatever will be the any, in spite of any status of the past outputs, this state is called as the indeterminate state, because in this state both the outputs tries to be high. That is, this case is not at all possible and it should be avoided. So now let us see the detail or the verification of this truth table. So this is the verification we can see in case 1. When the case 1 is there, that is S is 0, R is 0, let us assume that the previous output is 1 and complemented is 0. So let us see here, this is equal to 1 and this is equal to 0, and we are taking the case of S is 0, R is 0. So this flip-flop will function only when this enable is high. That is, we are taking this clock as the positive edge trigger and we are writing it here as the high, right? So this is a NAND gate, and as we know, the output of the NAND gate is high when any of the input is low. So as you can see, this is one low is there, 0, 1, 0. So this will be 1. Similarly, this output of 4th NAND gate will be high. Now, giving the feedback from this Q2 in NAND gate 2, this is 1 coming here and this 0 is coming here. Now find it out, 1, 0, 0, this output will be 1 and this 1 is coming here, 1, 1, 1, this is 0. So there is no change in the output. The output will be whatever is the previous output, that will come as it is on the present time, right? So the other way can also be possible, can also be verified, that if my previous output is 0, then what will happen? Let us see. If my previous output is 0 here and 1 here, and my inputs are 0, 0, clock is enabled 1, then what will happen? 1, 0, 0, this will be 1, this is also 1, and this feedback 0 is there and this feedback 1 is there. So 1, 1, 0 is there, 0 is here, 1, 0, 0, 1 is here. Similarly, you can see in the second alternative or second option, if it is there, then also when it is 0, 0, the output, there is no change in the output. Whatever is the previous output, that is carried over to the present output. Similarly, let us verify the second case. In the second case, S is 0 and R is 1, right? My enable is high. So in this case, let us assume that my Q1 is 1 and my Q1 bar is 0, right? Now let us find the outputs. This is 1, 0, 0. This will be high and this will be low. And this 1 will come here. This 0 will be coming here. So as you can see, this is 1, 0, 0. This will be 1, 1, 1, 1. 1 is coming here, 1, 0, 0. And this has to be 1. So there is a change. Now this change is carried over to this, fed back to this input. So 1, 1, 1, this has to be 0. Again it is changed. So this 0 is coming here. This is 0. So now 0, 0, 1. Now it has attained its stability and this 1 is here. Now it is okay. Now as you can see, when S is 0, R is 1, and if the previous output was 1, 0, Now at present, what will be my output? My output will be 0 and 1. As you can see, output will be 0 and 1. Now let us see this another case, assuming that the previous output is 0 and 1. Now let us assume this output is 0 and this is 1 and this is 0, 1, 1. Finding out the output, 0, 1 is 0, 1, 1, 1, 1, 0. This 0 is coming here, this 1 is going there. So this is 1, 1, 1, 0, 0, 0, 1, 1. It's okay. So now if the previous output is 0 and complement q bar is 1 and I am giving at the input 0 1, then my output is 0 1. But in case it is previous is 1 here, it is changed to 0. So in this case, when s is 0, r is 1, the flip-flop is set to be reset because this q output is 0. That's why it is set to be reset. Now let us verify the third case. In the third case, S is 1, R is 0, right? And let us assume that Qn is 0 and Qn bar is 1. That is previous 0 is 0, previous output is 0 and this one is 1, right? This enable is 1. So this is 1, 1, 1, 0, 1, 0, 0, 1 and this is feedback to this 0 and this is 1 here. 1 0 0, so it will be 1 here and this 1 will be here, 1 1 1 0 will be here, so this 0 is carried over to this here, 0 0 1. Now it has achieved stability. So now as you can see, if my S is 1, R is 0 and the previous output will be if they were 0 and 1, so now it has changed to 1 and 0, right? So now in this case, when S is 1, R is 1 and then my Q is 1 and the flip-flop is set to be set, right? Now let us see the other way also. If my previous output is 1 and this is 0 and I am giving here 1 0 1, so the output will be 1 1 1 0 1 0 1. This output is fed back to here, this is going there, so this is 0 0 1 1 1 1 0, so this is okay. So this the output is set to be 1 here and the flip-flop is set. Clear? So all the three cases we have verified. Now coming on to the fourth case. In the fourth case, let us, in the what is the fourth case? That S is 1, R is 1. Now I am assuming that my previous output is 1, 0, right? And my enable is high. So this is 1 1 1 0 1 1 1 0. This one is coming here 1. This 0 is coming here 0. 0 0 1 1 1 1 is here 1 0 0, so it is has to be 1. See, this both are going to be 1 1 0 0 and this both are going to be 1. That is not at all allowed. So this case is avoided in case of SR flip-flop. Clear? So other way also you can see that if it is 0 and if it is 1. Similarly, you have to verify all the flip-flops in all the types of flip-flops. It may be SR flip-flop, JK, D, T, any type of flip-flop. You can verify the truth table or you can make the truth table like this. SR flip-flop can also be used with these two inputs, preset and as you can see, we have provided the preset input at the NAND gate 1 and clear input at the NAND gate 2. Now what is the significance of these two input, preset and clear? Suppose the flip-flop is not enabled and we want to make the Q output equal to 1, then we will provide 0 logic or 0 input at the preset. We will get we will get 0 provide, we will provide 0 at the preset input and we will get the 1 as the output, so the flip-flop becomes set. So if we want to clear the output, means we want to make q equal to 0, then we have to provide 0 at this clear input, and we will get 1 here and 0 here. Like this, in spite of the whatever the clock is there, we can change the output as equal to 1 and 0 by providing the 0 voltage or 0 logic at the preset and input. You can also see these are the active low inputs, and in the diagram these are drawn like, in the clock diagram these are drawn like this. From the truth table you can make out the clock is 0 by making this preset equal to 0. Now the q is equal to 1. If clock is clear is equal to 0 and preset equal to 1, now the q is equal to 0 and the flip-flop is set to be clear mode, and when preset it is q equal to 1. Otherwise, when clock is high, then we have to keep this preset and clear equal to 1 for the normal functioning of the flip-flop. The behavior of the SR flip-flop can be very well made from the timing diagram. This is the clock pulse, this is the input SR, this is R, and we have to make the outputs Q and Q bar. So now the flip-flop is positive edge trigger. So at the positive edge of the, at this instant of clock, means when it is positive edge, rising edge, S is 1, R is 0. So the flip-flop has to set, means Q has to be 1 and this is Q bar equal to 0. Another instant when the change at the output will take place at the next positive edge of the clock. In between, though there may be a change in the input, but that is not reflected at the output. So the change will at the output will only take place at the positive edge of the clock. So at this point instant of time, S is 0 and R is 1. So now the flip-flop will become reset. So now see the clock Q is equal to 0 and Q are equal to 1. At the third instant of clock, it is here, S is 0, R is 0. So there will be no change in the output. Whatever will be the previous output, that will continue at the present output. So like this we can make out the outputs from the timing diagram. D flip-flop. D flip-flop is called as the delay flip-flop. Delay flip-flop means that it is providing the input at the output with some delay, and that delay is provided by the propagation delay or the operating time of these NAND gates which are being used in the flip-flop. As you can see from the diagram, delay flip-flop is made from the SR flip-flop by providing a NOT gate. Here this NAND gate is working as a NOT gate between S and R inputs. The rest of the circuit is same. From the truth table you can make out, if clock is enabled, D is equal to 0 and 1. So there are only, because input is 1, there are only two options. Either D will be equal to 0 and D will be equal to 1. So when D is equal to 0, we are getting output equal to, present output equal to 0. If D is 1, Q is 1. So when D is 0, Q is 0, our flip-flop is set to be reset. When D is 1, Q is 1, flip-flop is set to be set. So we are using the two cases of SR flip-flop, and these two cases are, if D is equal to 0, then S is equal to 0 and R is equal to 1. So if D is equal to 1, S is equal to 1 means, and R is equal to 0. So we have already verified these truth table of these two cases. So like this you can see, if D is equal to 0, it is reset. We are getting the output as 0, 0. If D is equal to 1, we are getting the output as 1 and 1. So that's why it is called as the delay flip-flop, because there is no change in the output. Whatever will be the input, that is shown at the output, or that is passed on to the output with some delay. Rest is same, and we are using these two cases of the SR flip-flop, and S is 0, R is 1, and S is 1 and R is 0. The D flip-flop timing diagram, you can see this is a clock signal, this is the D input signal. At the positive edge, if D is 0, output will be 0. at the next positive edge, because in between whatever change is taking place at the input, that is not reflected at the output. The change will only be reflected when the flip flop is enabled, and that enabling is there at the positive edge of the clock. So when you see at the second instant d is 1, so output will be 1. At the third instant, that is positive, at the third positive edge, d is 1, output is 1. So the fourth, d is 1, output is 1. Though in between it has become 0, but doesn't matter, because in the this flip flop is still disabled. So when this is at this instant, d is 0, so now see q is 0. At this instant, another instant, when positive edge of the clock comes, this is high, so the output is also high. Like this we can make out the outputs from the timing diagram. Next comes the jk flip flop. We know that in case of SR flip flop, in the case 4, when S is equal to 1 and R is equal to 1, that condition was avoided, because in that case both q and q bar both tries to become 1. So to remove that limitation of SR flip-flop, what we have done, the rest of the circuit is same. We have just provided this q and q bar as feedback at these initial or the input gates also. So q bar is provided here also, and q is here. Similarly, q bar is here and q is also provided at the input gates, which was not there in the SR flip-flop. So you can see if j is equal to 0, k is equal to 0, j is 0, 1, 1, 0. So first three cases are similar to the SR flip-flop, that is there is no change when j is and k are both are 0. When j is 0, the flip-flop is reset. When j is 1, flip-flop is set. But the condition was that if j is equal to 1, k is equal to 1, then what happens? Here, in spite of this modification, we are getting that is there is a race around condition. Race around condition means that both the input goes on changing till the clock pulses, till the flip flop is enabled, or if it is a level edge triggered flip flop, so for this whole period the flip flop output will go on changing from 0 to 1, 1 to 0, like this. So the output is not stable for this clock period, and it is uncertain. So this condition is called as the race around condition. It is make on racing from 0 to 1, 1 to 0, 0 to 1, 1 to 0, like this, for this whole enabled period of the flip flop. So the four cases which we have seen, that is j is equal to 0, k is equal to 0, j0, k1, j1, k0. So you can very well verify these um, cases from the flip flop. So let us see what happens when j is 1, k is 1, and let us suppose this is my previous output is 0 here and 1 here. This clock is 1, this is 1. So this 0 is here, this 1 is here, 1, 1, 1, this 0 will come here, this 1 is here. This 0 is coming to this side, this 1 is to this side. So 1, 0, 0 means this has to be 1. Now this 1 is coming to this side, 1, 1, 1, this become 0. So this 0 is reflected here, 0, 0, 1. Now as you can see, this final output is changed and this is fed back to this side. So this also changes to 1 and this changes to 0. So when this becomes, so this becomes 1, this becomes 0, again 1, 0, 0. So it again changes to 1. So when it is changes to 1, this is changes to 1, 1, 1, 0. So see, now again it has changed from 1 to 0 and this is from 0 to 1. So earlier it is, so like this goes on changing from 0 to 1 and 1 to 0, because this output is also changing the my input, because it is fed back at the input gates also. So like this you can verify the JK flip-flop truth table. So as we can see that this is a limitation of JK flip-flop, that a race around condition is occurring at the fourth case when J is 1, K is 1. So now how we can remove it? So we can remove, or this can be avoided by using the a clock input that is at logic 1 for a very short period of time, or the level of, or the clock pulse should be the high time of this clock pulse, or the level, if this is level I triggered, it should be less than the propagation delay of the gates. Or another method is that we can use a master slave JK flip flop. We will study in coming slides. So the behavior of the JK flip flop from this timing diagram, as you can see, this is a clock, this is J input, K input, and we have to make out the outputs Q and Q bar. So we have to see the positive edge only, positive edge, and this is 0, this is 0, so no change will be there. Let us suppose previous output was 0 and 1. So at the next instant, the J is 1, K is 0, so the flip-flop will become set, that is Q is equal to 1, so it is 1 and it is 0. At this instant, this is 1 and this is also coming to be 1. At 1 and 1, we are saying that it is going in the toggle mode, so it is going from 1 to 0 and this is from 0 to 1. So we have to just remember the timing diagram or the truth table of the flip-flop, so we can very well make out the outs from the in the timing diagram also then. So in at this instant, J is 1, K is 1, so the toggling will takes place. It is going from 0 to 1 and this is going from 1 to 0. At this instant, it is becoming 0, this is also 0, so no change. So this 1 will continue, this 0 will continue. At this instant, there is 0, 0, no change, so this 1 will continue, this 0 will continue. At this instant, you can see this is 1, this is high, this is high. So when both are high, the toggling will takes place. So it is from 1 to 0, going to from 1 to 0. So this is from 0 to 1. At this instant, J is 1, K is 1, again toggling will takes place. So this is going from 0 to 1 and this is from 1 to 0. So this is the timing diagram from positive edge triggered JK flip flop. Positive edge triggered means at the positive edge of the clock, the change at the output will occur, or the flip flop is enabled at that instant. So coming to the master slave JK flip flop, to remove the limitation or the race around condition in JK flip flop, we are using the master slave JK flip flop. As the name suggests, it is a master and a slave flip flops that are being used. So first one is the master and second is the slave. Why it is called master? Because first it operates, it gives the output, then it becomes disabled, and when this master become disabled, slave becomes enables. So when master is enabled, slave is disabled. When master is disabled, slave is disabled. Like this we are getting the output. Why this happens? Why we are using this concept? Because this output is and is available at the initial input, at the initial input gates. So if both are enabling at the same time, so whatever change is occurring at the output, that is at once will reflect it at the input, and that will again further change the whole output. So the output then will not be stable. So to make the output stable for a particular combination of the input, we are using a inverter in between the clock of the two flip-flops, master and slave. So when master is enabled, master clock is high, this will be low. Like this it will happen. So first master gives the output, then this output is passed on to the slave, and the slave will start operating when this become high. When master is disabled, slave is enabled, and then it gives the final output. It is then going back to the master, but this will not affect the final output because the master is disabled. So whatever change is occurring at the input of the master, though it is as it is not enabled, it is disabled, so it will not affect the further operation of the master slave JK flip flop. These are the JK flip flops, right? And this final output is fed back to the initial input. This is the block diagram. You can see this is the master, this is the slave, and this is J input, this is K input, right? And in between, this is the major point that you have to remember, that in the clock pulse this is a NOT gate is being used, and this is only removing the limitation of the JK flip flop. From the truth table, you can see when it is enabled, J is 0, K is 0. First three are cases are the same as it is they are coming. Now in J and K flip flop, when J is 1, K is 1, we are getting the toggle state. Toggle state means that the complement of the previous output we are getting. We can also verify this last state here in master slave JK flip flop. You can see, if let us suppose if J is 1 and K is 1, clock is enabled in master only, and we are assuming that this is 0, this is 1, right? And here also this is 0, this is 1. So when this become 1, because Q bar is coming here, this Q is coming here 0. So 1 1 1, this is 0 here, 1 1 1 0, it will be 1 here, and we are assuming 0 here and 1 here, so this 0 is here, this 1 is going to this side, 1 0 0, so this will change to 1. This 1 1 is here, 1 1 1 is 0 will be here, so 0 is coming to this side, so 0 0 0, 1 is there. So now we are got, let us say this is QM and this is QM bar, so this is 1 and 0 at this side. Now this is passed on to the slave at 1 and 0, but it will not work until this becomes 0, then this will become 1. So now 1 1 1, this becomes 0 1 0, 1 0 0, this become 1. Now this 1 0 is coming here, this 1 is coming here, 1 0 0, this become 1, this 1 is occurring here, 1 1 1, this becomes 0. See, the output has changed from 0 to 1 at the Q, and the complement has also changed from 1 to 0. Now this is going to here, 1 here and 0 there, but it has no effect on the output here, because this master is now disabled, right? So like this, the master slave JK flip flop removes the limitations of the normal JK flip flop. Coming to the last flip flop, that is the D, that is called as the toggle flip flop. As we have seen that the D flip flop, that is called as the delay flip flop, that is made from the SR flip flop. So T flip flop is made from the JK flip flop. By joining the J and the K input and becoming a T input. So we can have two cases when T is equal to 0 and T is equal to 1. So when T is equal to 0, J and K will be equal to 0. When T is equal to 1, J and K both will be equal to 1. So we are using the case 1 and case 4 of JK flip-flop. So the outputs will be, so we know that in case 1, when T is equal to 0, there will be no change. Whatever will be the previous output, that will be coming at the present output. If T is equal to 1, then toggle will takes place. Whatever will be the previous output, complement of that will occur at the present output. Like this we can verify. So this is the block diagram of a T flip-flop. Clear? So this is the behavior of T flip-flop can be made from the timing diagram. This is a clock pulse, positive edge triggered flip-flop is there. T is 0, Q is 0 because no change is there. For at this instant T is 1, toggling will takes place, so it has changed from 0 to 1. Now at this instant T is 0, no change will takes place, so 1 is continuing. Again at this state 0 is there, at this instant 0 is there, so no change, 1 is there. At this instant 0 is there, no change, 1 will continue. At this instant positive has triggered, you have to see just, right? So 1 is there, mean toggling have to takes place, so it has changed from 1 to 0. Similarly at this instant it is again 1, again toggling will takes place, so it is changing from 0 to 1. Like this we can make the output from the timing diagram. Now, what are the applications of flip-flop? There are many applications, and the most popularly for flip-flops are used in registers for storing a big number, as counters for counting purposes, as a memory, as a latch, as a bounce switching elimination switch like a switch, and frequency dividers, and many more. So this is the one of the reference I have taken. Thank you. So if you have any query, any doubts, you can write in the comment box. And thank you for watching this video till end.